All right, theorem 10.12, this is the first theorem in section 10.4, and it says, I grabbed the wrong notes again. Here we go. If tangent and chord, if a tangent and a chord intersect, okay? Tangent and a chord intersect. Then I'm gonna write the formula and then we'll label the circle so that we know what we're talking about here. And the measure of angle 1 equals 1/2 the measure of arc AB, and the measure of angle 2 equals 1/2 the measure of arc BCA. All right, so this is what it looks like. Let me just erase this. Draw a little smaller circle. We got something that looks like this. We got a tangent coming across here and crosses here. And we got this chord. Remember, chord runs on the inside from one side of the circle to the other side of the circle. So we'll label this point A, B. We got a point C over here just so that we can figure out what we mean by BCA. We're talking about that arc there. So this is 2, and that's angle 1. So when you guys get done drawing that, we'll kind of talk through it. So when you look at it, just to make sure that it makes sense. You guys are still drawing. You're being very artistic, aren't you? It's got to be just right. Big circle. I see somebody's got the quarter out there. I'm going to trace around the quarter. Not really.
A nickel would be better.
A nickel. Yeah, I mean, it would have the little ridges, right? Actually, what would be best, what I find to be best, is one of those like gold $50 or dollars, you know, because they don't have the ridges on them. Those work very well. All right, so the measure of angle 1 is basically half the measure of this arc right here, right? AB. And then there's an arc over here. It corresponds, this is supposed to be a B, by the way. I don't know what that's almost like a 7 carrying a backpack. It's sort of what it looks like. It's supposed to be a B. That doesn't really, that looks like an A that's got problems. Back issues. All right, there we go, B. So the measure of this angle here is 1/2 the measure of this arc, right? So the arc that's kind of associated with each side of the angle, or the angle of each side on each side of the chord, that angle is half the measure of the arc on that side of the chord. Does that make sense to everybody? So let's do a couple of examples. Make sure that we can properly apply it. So if we look at the first one, which is just simply, and it's really easy. So they give us this, and they give us this, and they say this is angle 1, and this is 150, and I want to know what the measure of angle 1 is. Well, we say no problem. The measure of angle 1 is simply 1/2 the measure of this arc right here, which is 150. So the measure of angle 1 is 75 degrees. Okay? Does that make sense to everybody? Excuse me. What if I gave you the same problem and I asked you to give me the measure of angle 2? Who could do that? Cal, what you got?
It should be the same because look, the chord in the middle looks like a diameter.
It may look like a diameter, but is it a diameter? 80.
The line that's running as a point of tendency, that's perpendicular to the other line, which means it is diameter, right?
Not necessarily.
Has to be 180.
No, we don't know that that's forming, we don't know that it's perpendicular. Yes?
They're vertical angles, right? Well, not vertical angles, but they should be supplementary.
No, what do you got, Mary?
That measure right there would be 180 to be a diameter, but you could still subtract it from 360.
You have to subtract it from 360. That's really the key here, right? We know the measure of the entire circle is 360. And so if this thing's, it's definitely some portion of the circle. We just don't know if it cuts the circle in half. What is it?
Measure of angle to be 105.
105. So the measure of this is what? The arc?
210.
210. Yeah, 210. So this has got to be 210 degrees because, like Mary was saying, these have to add up to 360, right? And so what Paul did is he took this half of that and he said half of 210 is 105. So the measure of angle 2 equals 105. So a few more steps to that one, right? It's still not hard. You just have to remember, you can't assume, I'm glad I asked that question, because you can't assume that this guy is perpendicular, because there's nothing there designating that it's perpendicular. If it was perpendicular, you're right, it would be a diameter. We had a theorem that talked about that, right? But we don't know with this one here. But what we do know is the other side had to be whatever 360 minus 150 is. Okay? All right, so the other problem is similar, except they give us the measurement of the angle instead of the measure of the arc, and they say, what's the measure of the arc? So, in other words, if I were to give you this isn't drawn to scale at all, but let's say I gave you this as 130 degrees, and I asked you to tell me the length of this arc, the measure of this arc right here, then again we would use our formula and we would say 130 degrees equals 1/2 whatever the measure of that arc is there, right? We'll just we'll say A, B, C, so we know what we're talking about here. And so then the measure of ABC would have to be 2 times 130, which would be 260. Make sense? Any questions about that? What I did there? Just plug it in for these formulas. All right, let's, unless you're going to stop me, I'm going to keep moving along until I see somebody raise their hand. Say, I don't get it. Let's talk about two chords intersecting the interior of a circle. So this is theorem 10.13. And it says if you've got a circle that looks like this, that's more of an ellipse. I'm gonna make it more circlish. That was terrible. I was doing really good until right at the end, and I added this overtime, guys. Don't worry, in 25 years, this will be perfect. Practice this enough. There we go. All right. So this, we got that. We got A, D, B, C, 1 and 2. And so what this says is if you have two chords that intersect interior of a circle, it's our little symbol for a circle, then we can say the measure of angle 1 is equal to 1/2 the measure of arc CD plus the measure of arc AB. And then the measure of angle 2 is equal to 1/2 the measure of arc BC plus the measure of arc AB. It's out of the way for on this side of the room. So if you just kind of look at it, you can see based on what this says here, it'll always be the arc that, like, if this is angle 1, we remember that these are vertical angles, so the measure of that's also angle 1, right? So those angles that are the same is the arcs that's formed by those two angles. You add those together and take half of that to get the measure of the angle, right? So if we were to do a problem related to that,
You could just take the measure of CD to get it, looks like, or the measure of AB.
say that again.
If you took the measure of, oh, but if it's not in the middle, then
It's not in the center, right?
Yeah.
Yeah, exactly. Yeah, that's why we have to have this one. So let's do a problem, looks like this. They tell us that we've got something that looks like that, and they say this is X degrees, and this is 174 degrees, and this is 106 degrees, and they just said find X. Then we could say, just plugging in that theorem directly, the measure of angle X is going to be equal to 1/2 this arc, which is 106, plus the other arc, which is 174. So 280, and half of that would be 140. So the measure of angle X would be 140. So everybody see that? What if it had looked like that? Could we have found X?
no.
No, we can't. We don't know anything about those other angles. There's no, since it's not, we don't have a diameter or something that would tell us that it's perfectly cut in half or something like that. There's just no, we don't know enough information to know what's going on with these two angles here. Okay? Any other questions? Or any questions? I guess you didn't ask a question yet. Who wants to go on and do theorem 10.14? You guys on board with that? 10.14? You good? Instead of a pop quiz, let's go over theorem 10.14, okay? All right. I like the way you guys think.
We do too.
All right, so theorem 10.14, we got a bunch of drawings with this one. But the basic idea is the same for all of them. This is where I said you needed to remember the definition of a secant versus a tangent. And you basically have three drawings that for one circle here, move this over here. For one circle, you've got a tangent out here, and you've got a secant right here. And so you can label points A, B, and a point C down here. And this is angle 1. And so you've got this angle that's formed by the tangent and the secant outside the circle. And but there's a relationship between the length of these line segments, or not the line segments. Sorry, I'm looking at the next theorem. These arcs that are basically. Let me see if I can use the different colors to label these a little better. And all of these they're very similar, even though some of them have two tangents and some of them have. That's not really. Me and my colorblind self, I don't even know if I'd be able to see that from the back of the room. That's the best I got. Let's do it blue. So it's related to those, the measure of those arcs right there, okay? Angle 1 is. And that relationship is this. Theorem 10.14 says that the measure of angle 1 is equal to 1/2 the measure of angle, the measure of arc BC minus the measure of arc AC, okay? So here's what I want you to understand, this theorem is going to be similar in that no matter whether we have two secants, two tangents, or a tangent and a secant, you will always have a big arc that's formed by them, and you'll always have a smaller arc, okay? And this angle that's out here is always going to be half of the measure of the bigger arc minus the measure of the smaller arc. Okay? So if I were to draw this figure here, where we have, now we're going to have two secants, okay? So both pass through the circle like that. And if I were to measure, if I were to call this angle, just so that we don't get confused, I'll give them different numbers. We'll call this angle 2. We'll call this, I'm kind of doing these out of order, I just realized. W, X, Z, Y. Then we could say that the measure of angle, that's fine, I'll do 2. Measure of, just don't let me mess this up. Measure of angle 2 equals, you guys double check me here, 1/2 measure of angle arc XY minus measure of arc WZ. So you see how it's really the same thing? The measure of that angle out there is always 1/2 the measure of the big arc that's formed by the secants minus the smaller arc formed by the secants. Okay? So then we have one other scenario, and that other scenario is where you've got an egg, it's supposed to be a circle. You have a circle, and now we have two tangents. So I've got a tangent here. I didn't quite hit the circle. What's going to happen? Still didn't quite hit it. We're just going to tell you what we're going to do. We're going to just make it work. I'm going to make that a little bigger. There we go. We're going to put a point P right here, point Q right here, and a point R right here. We'll label that angle 3, and then we can say that the measure of angle 3 is equal to 1/2 the measure of, again, the big arc, which is PQR, minus the small arc, which is just PR. So does everybody see how it's the same thing? Each time it's just different lines that form those, the big arc and the small arc and the angle. Any questions about the theorems, or the theorem itself, the way the theorem is defined? No questions? I'm gonna text my wife and ask her to bring me a coffee. I just feel like I'm recording with my phone. She's got to bring my youngest son to the next class anyway. Duncan's right on the way. No questions about the theorem? All right, let's do one that actually is a word problem. Since like I said, word problems are always kind of, students tend to get confused with word problems. It says you're on top of Mount Rainier on a clear day. Does anybody know where Mount Rainier is?
Washington State.
It is. You can see it from Seattle. It's beautiful. But unfortunately it rains in Seattle most of the time, so You have to be there at the right time of the year to be able to get a really good view of it. We were there one week and it like rained only one day. It was amazing. Very thankful to the Lord we were able to see it. But anyway, you're about 2.73 miles above sea level, it says. Find the measure of the arc CD that represents the part of the earth that you can see. So if you're on top of Mount Rainier, you're 2.73 miles above sea level. So they've already drawn this diagram. I was like, how are we supposed to know 4,000 miles? They just gave us that, right? So 4,000 miles to the center of the earth. So here's our drawing. Here's Mount Rainier. Mine looks much better than the one in the book. Just
So
saying.
much.
Here's a point A. And we've got these lines here from the top of Mount Rainier. That's not much of a line. The wind blew while they were trying to put the cable down from the top of Mount Rainier.
That's not good.
Alright, let's try again. That's a little better. Right? And they tell us that this is 4,000 miles. So the point from here to there, they tell us that's a right angle. That's 4,000 miles. All right, so that means that's what? A radius. It's a radius, right? Because it forms a right angle with this tangent right here, then if we extend this on out, it would be a diameter. So that's the radius, right? And so if we draw a line from here that goes straight to where Rainier is, and clearly this is not drawn to scale, they told us that you're 2.73 miles above sea level at the top of Mount Rainier. And so this total distance here, all of this together, like from here all the way to here, is a distance of 4,002.73 miles. Okay, everybody tracking with me so far? See how we got that?
Wait, is the point A, is that like in the middle of the,
That's in the center of the earth. That's in the very center of the
so
circle.
if this is the mountain going like that, it's like this, like if it's going up like that, it's
Uh-huh.
like,
It's a cone. Well,
It's like down from the center of the top of the mountain, like all the way down through the center of the earth.
gotcha.
Does that make sense?
Oh, so what's on top of the circle, that's only what you can see of, wait,
This is the earth.
oh.
So it goes
This is just the
oh,
mountain sticking up on
gotcha.
top.
So,
It's
Got it?
totally to scale, like 100%.
Yeah, I didn't draw it. Yeah, it's not drawn to scale.
Even in the
Very
book. Even in the book.
well. Even in the book, yeah, you're right. It's not drawn to scale in the book at all. Oh, they say that, not drawn to scale. There you go. So anyway, our point is when we see something like this, it's like, okay, wait a minute. How am I going to use the theorem that I just learned, right, in order to solve this problem? And so they said that the measure of angle CBA is 87.9 degrees. CBA. This is C. This is B. That's A. And they were able to figure out the measure of CBA to be 87.9. How did they do that? Any idea? Aiden?
Your metric function ratios.
Your trig functions, right? So if since this is a right angle, then we know we can use our trig functions to figure out what this angle is right here, right? So we've got this big right angle. Here's our right triangle. I mean, we've got a big right triangle. It goes from here down here and over to here. So since we know this big distance here, which we just said was 4,000 2.73 miles. Then we can figure out this angle using what trig function?
Sine.
Sine is opposite over hypotenuse. The opposite side is 4,000. The hypotenuse is 4,002.73. So sine of some unknown angle, we'll just label it, we'll just say angle CBA. We'll say what they're saying here. Angle CBA equals 4,000 over 4,002.73. And so if we do the math for that, if we punch that in our calculator, we'll get some decimal value. Somebody want to punch it in for me and tell me what it is?
.99931.
3 nines?
Yes, sir.
3 1. All right. Then how would I figure out the measure of CBA from that? I would take the inverse sine. Remember that? So you're going to do sine inverse of that. So the measure of angle CBA is equal to the sine inverse of 0.99931. And when I do that, I get about, I should get this value here, which is 87.9 degrees. Does everybody get that? Basically? Yep. All right, cool. So now that we have that, now we can figure out this entire angle here. Because what's that entire angle? Does everybody see that the entire angle would have to be double that? That this line as it comes down here bisects that, so that this entire angle, that one there, has got to be that times 2. So 87.9 times 2 would be the measure of angle CBD is equal to 175.8 degrees. All right, I'm sure that at some point we're going to be able to use our theorem that we just learned. But so far we haven't used it, right? So they said, let the measure of angle CD, which is this, not angle, the measure of arc CD, which is this. Let's try to use the blue and see if we can highlight that arc. So this is the arc right there. Because what did the problem actually ask us for? Find the measure, or so just find the measure of arc CD that represents the part of the earth that you can see from the top of Mount Rainier. So based on the curvature of the earth, that would be the distance that we could see from the top of Mount Rainier. And we can find that now because basically these lines here were tangent to the outside, and we had this theorem here that said, well then this angle up top is equal to 1/2 this angle here, I'm sorry, this arc here, 1/2 this arc here minus this arc here, right? How are we going to figure that out? If we label this, we'll label this blue thing, this blue arc X. But we don't know what this distance here is, so how are we going to find out what X is? We basically we know that this angle here is going to be half of this minus this. So you can only do this particular trick on the tangent problems, when you've got a line like this. Do you guys agree that if I'm looking at this problem right here, that the measure of arc PR is going to be equal to 360 minus the measure of PQR? Does everybody agree with that? And so the trick that they use then for this is that we don't know what the distance of this is, but we know that the distance of this is 360 minus X. All right? So now let's take all of that information and put it together to solve the problem. So using our formula right here, we can say that the measure of this angle, which is that angle there, which we determined to be 175.8. So 175.8 is got to be equal to 1/2 the measure of the big arc, which is 360 minus x. That's the measure of the big arc, minus the measure of the little arc, which is x. So did I lose anybody when I wrote that down? I lost you? Tell me where I lost you.
So you just use, so 360 minus x is the DC arc, the big one.
This one right here, that's right. So this right here, let's see if I've got it. Let's see if this red won't work. Yeah.
Okay.
This guy here, we know that the distance of this guy
Okay, and then
is 360 minus x, right?
and then the other one's just x.
Yeah. Does that make sense now? So this was the 360. We'll kind of put some, we'll put that around that and show that was the measure of the big arc minus the measure of the small arc, which is just x. Whew! Wow, this is intense, right?
So long.
I don't know why I picked this problem. What's 175.8 times 2?
It's 351.6.
351.6 equals 360 minus 2x, right? I got rid of this 1/2 by multiplying the whole thing times 2. So that gave me 351.6. And I went ahead and took this minus x and combined it with the other negative x. So I got negative 2x there. So then we'll bring the 2 over to here and say that 2x equals, what's 360 minus 351.6? Just 8.4. All right? Did I do that right? And so then if we divide both sides by 2, we can say that x is equal to 4.2. Is that what they got? Yes. So 4.2 is the measure, it's actually the degrees of this arc right here. The measure of arc CD. That was a lot of stuff in that, right? There's no way I'd give you a problem like that on the test.
Oh, that's good.
But it is important, it isn't, like in hindsight, I didn't go over that problem before I did it in class, so I was like, we'll just do a word problem, that'll be fine. But that was really involved.
You're like, everybody, I don't understand why students get so stressed out over it.
Yeah, right, there was a lot to that one. But you see, at the end of the day, we were just using our basic theorem, right? Our theorem right here. And so just make sure that you understand with these, whatever this angle is that's outside of the circle is going to be 1/2 the measure of the big arc minus the small arc that's formed by the lines. Okay? Any questions about that? I had this crazy idea we might get through 3 sections until I did that long problem there. No questions? Okay. The energy's really gone down after that. We gotta. Let me see if I can bring the trash can again. I'm just kidding. All right. I need to text my wife and say, bring us all coffee.
Yes.
All right, so let's go on to the next section. And in that section, we've got 2 chords that intersect the interior of a circle. So this is theorem 10.15, sorry, 10.15. So we've got a circle here, and we've got these chords that are inside the circle. E is where they intersect, the point where they intersect. A, B, I don't know why I've written these in such a strange order. Maybe I copied it from the book, I don't remember. So if two chords intersect the interior of the circle then we can say that EA times EB equals EC times ED. That's right. Yes. So two chords, again, don't get confused. This is not the center point of the circle, right? We just have two chords that are intersecting somewhere in the circle. And if that happens, then we can say that this, for the line, for the chord, you know, each part of the chord, if you multiply each part of the chord together, the measurement of the line segments that are formed by the intersection, this times this is going to equal this times this. That's what we're saying. All right? This times this is equal to this times this. So that's what it boils down to. So if we have a problem like this, and we've got something that looks like this, and we say that 3, 6, 9, and I asked you to find x right there, you would just say 3 times 6 is equal to 9 times x. All right, or 18 equals 9x, and so x equals 2. Okay? It's pretty straightforward, right? Easy enough to apply. Even if you're the type of guy that staples his test back together after he's folded it and turned it in. That's easy, right? All right, let's do theorem 10.16. And theorem 10.16 says for two secant segments. So we've got something that looks like this. And we've got A, B, C, D. We'll label this E out here. Does everybody see that AB and CD are secant segments? They're segments of the secant. So for two secant segments with the same endpoint outside a circle, then what this theorem says is that EA times EB equals EC times ED. So A and B, or AB is a secant segment, but EA is a secant segment as well, right? It's just a segment that's formed, that's external to the circle, and here's a segment of the secant that's formed that's internal to the circle. So what this is saying is that if you have this kind of scenario here, you take the external segment and multiply it times the entire secant, and that's equal to the external segment of this one times the entire length of the secant segment. All right? Any questions about that? One more, which is kind of similar but involves a tangent segment versus a secant segment. Theorem 10.17. And it says, we got this, and now we got a tangent right there, tangent segment, and then a secant segment, C, D, E, A. So here we have, if a secant segment and tangent segment, and why are we calling them secant segments and tangent segments? Just because, remember when we drew secants and tangents before, they were lines, right? That went, just kept going here. So like that, and then maybe we had a secant, it looked like that, right? But it's a segment because there's an end point there, it doesn't keep going. So this entire thing in this one, EB, is a secant segment, but then this part here is a segment of that secant segment, and this part here is a segment of that secant segment. So the language gets kind of weird, but I just wanted to make sure you guys are following it. So here, EA is a tangent segment because it doesn't continue to go, but it is tangent to the circle, and then ED is a secant segment, and EC is a segment of that secant segment. And CD is a segment of that secant segment. Try to say that 3 times really fast. If a secant segment and a tangent segment share an endpoint outside the circle, then we can say EA squared equals EC times ED. So let's try to apply theorem 10.16 and solve for x right here. So who can set this up for me based on that theorem? Yes?
So wouldn't it be 9x equals 11 times 10?
No. No, think about what this says here. EA, which is the portion of the segment here, times EB, the entire length of the segment.
Oh yeah, so
Right.
it's 10x equals 9 times 11.
Not quite. All right, you're right about and it's not even 9 times 11. It's EA, it's this portion here times the entire length here. So it'd be 9 times 20. Do you see that?
That makes sense.
So 9 times 20, which is 9 plus 11, equals 10 times 10 plus x. And that's why I wanted to ask you guys first, because that's an easy mistake to make, right? You forget to add those together when they've drawn it like this. But it's the length of the portion that's outside the circle times the entire length of the segment. So you have to add those numbers together to get that. So this is 180 equals 100 plus 10x. So 80 equals 10x. So x equals 8. Is that right? Yep. So any questions about how we did that one? Does that make sense? at the risk of taking another 30 minutes and making my class run long, I'm going to try to do one more word problem. This one looks a lot simpler. We have an aquarium tank. You're standing at point C, which is obviously outside the tank, because if you're inside the tank, I hope you've got gear on to be able to breathe, right? So here's the aquarium tank. And has anybody, by the way, ever gone like to the Georgia Aquarium, been able to go in where the whale sharks are? Have you actually been diving with the whale sharks?
Not diving.
Okay. I don't know if they still do that, but you used to could pay and actually go in there with them. But
They do still do that.
Yeah, I've seen
Did it?
people.
They do
Okay.
snorkeling, you have to have a driver's license.
right, yeah, you have to do all of that. So I've never done that. Seems really cool though. All right, so they do this drawing that looks like this. And then we'll draw this like this. So here's this point C where you're outside the tank. And this is point B. And this is point E. And this is D. And they've got the center point here labeled, and this is R, and this is R. Right, the radius of our circle. And they tell us that this is 20 feet, and this is only 8 feet. Again, my drawing is clearly not to scale. So the distance from you to a point of tangency on the tank is about 20 feet. So this is the point of tangency. Well, how do I know that's the point of tangency that they're talking about? This distance here? Because this line is tangent to the circle, right? And it tells us that we're 8 feet from the aquarium tank. So if we just drew the shortest line we could from where we are to the aquarium tank, it would be 8 feet. Estimate the radius of the tank. So can we find R based on that information there? So we're using theorem 10.17. Who can set this one up for me? Someone else. 80.
20 squared.
So 20 squared. So realize what he did. Our EA squared right here, right from that theorem, is basically the 20 feet in this problem. Okay, good.
Is equal to 8 times 8 plus 2x.
So 8,
Or 2r, sorry.
2R, yeah. 8 is our EC right here, right? Times 8 plus 2R. Why, somebody besides Aiden, why would this value here be 8 plus 2R?
Because we want to do the full secant instead of just.
Yeah, the full length of the secant segment, which is this 8 plus this R plus this R, right? So that's where we get that value from. So this would be 400. You know, I'm going to go ahead and divide the 400 by the 8. That makes the math a little easier. So if I do this, if I go ahead and divide by 8, and I know that top part is 400, then this would be 50, equals 8 plus 2R. And so that's 50 minus 8 is 42, equals 2R, and so 21 equals R. Is that right? 21 feet? Yes. Why did they say it's roughly 21?
Because it said it's roughly 20 feet.
Oh, they didn't tell us. Okay, the point of tangency is about 20 feet. I got you. Okay. So yeah, technically we would need to put the feet on here for this problem to be correct, right? I've been pretty lenient with you guys using your units so far, but one day I could just snap and like count points off for you not putting your units down. It'd be bad, you know. Like test would go from a 97 to a 32.
Oh gosh.
How
many units are
coming?
Yeah.
Does everybody understand that? Does that make sense? You got that? You know, we really don't have time to go into the next section. What do you mean? Paul's like, yes, it means we're going to do more problems like this. Is that what you were saying? That's what your cheering was?
No, it's
No?
just, we have one less homework.
Yeah, that would have been a lot of homework, right? 3 sections. You guys couldn't handle that. You guys ever had 3 sections of homework in here? Was it pretty
I think
rough?
we have.
It was a bad week, huh?
Yeah.
Yeah.
It was
It's like-
easy sections.
It was easy sections. Okay, good. So I could do one more example, but it's basically the same thing. I think. Example 4, same kind of thing. Just remember that you got to do 4 plus x. Oh, wait a minute. Whoa. Wait a second.
Slow down there.
Wait a second. So why is that one? Oh, it makes you have to. You got to use the quadratic formula. It's been a while since you thought about that, huh?
Yes.
Yeah. Gives it kind of a bad taste in your mouth, Mary? Wow. Quadratic formula. Let's just see if you guys could give me what the quadratic formula is. Does anybody know? So that's if you've got something that's not like a simple quadratic, right, which you can easily factor, and your quadratic is in the form ax squared plus bx plus c equals 0, then you could use the quadratic formula to find out what x is. And so it was x equals, is it negative b? Negative b plus or minus the square root of, it's all over 2a, isn't it?
Yes.
Is this 4ac?
Yeah, that sounds right.
Is that right? Let's see. 4. Wait a minute. No, that's not quite right. It's negative b plus or minus the 4 squared. It must be b squared right here. B squared. Is that right? B squared minus 4ac? When I don't know, my voice gets really high. 4ac? 1. That's a, c. Yeah, that's it. Negative b plus or minus the square root of b squared minus 4ac over 2a. So that's the quadratic formula.
That's
So-
not complicated at all.
Definitely not.
But you guys could do that, right? If we had all the other numbers, couldn't you plug that in and work that out? I think you could. I have complete confidence in you. So I'm just going to write that down, not because I'm planning to give it to you on a quiz or a test, but because you may have a homework problem that uses that. And I just want to make sure that you recall what it is. Okay, so some of these problems, because of this one right here, because of this guy that's got EA squared, it's possible you're going to have a square term in there, and so you may have to use this in order to solve for x. All right? Okay, I'm going to let you guys out a little bit early, and you have a good day.